Well, hello. This is Exploring Creation with Physical Science, a third edition, Module 4. All right. So we're going to dive right in and go over some vocabulary. The first one we've got is called chemical formulas, which is basically a recipe. We've got the ingredients, we got the amounts, and you just exchange those words for elements in a compound and their amounts, and you've got yourself, here's an example of a chemical formula you might be familiar with. So we know we have 2 hydrogen and 1 oxygen molecule in the compound H2O. All right, next up we have chemical equations. A chemical equation is when we build that. It is taking the chemical formula and breaking it down into all of its parts and how we got it. And so we have, for instance, carbon and plus oxygen equals carbon dioxide, which is also known as CO2. So when we take carbon plus oxygen, the whole thing is called the equation, all right? This side of the equation, sorry, it's not longer. This side of the equation is called the reactants. This side, after the equal side, familiar math term is called the product. Okay, so the products are the new substances that are formed as a result of the chemical change. So reactants, products, whole thing, chemical equation. All on its own, this would just be a simple chemical formula. All right, so let's see if I can pause this. It's going to really be hard to pause this over and over with it facing the other way. I have yet to figure out a good way to do this. All right, so if you hear the word diatomic, you're going to break that down into di meaning 2 and atomic meaning atom. Okay, so it really quite literally looks like, I don't know, butt cheeks. And we are looking at 7 different homonuclear, homo meaning same nucleus inside of these, and diatomic molecules. And that means that they come in pairs. So hydrogen, fluorine, oxygen, chlorine, iodine, bromine, and nitrogen all come in pairs like this. And so when we start trying to make these recipes, as we were just talking about, or chemical formulas, equations, even better yet, equations, we will find sometimes that the things that we are adding up on our reactant side, hydrogen, will come sometimes as usually, I think always, yes, hydrogen is a diatomic molecule. It will come with a 2 down here below it, meaning it came as a pair of atoms connected together. If we add hydrogen and oxygen, which also is diatomic, it will come as a pair. If we want to make water, or let's just make it equal water, H2O, something is not right here. We're not able to have, we need to have 2, we need this to balance on both sides of the equation. And there's not 2 oxygen here, and there is up here, so something's not equal with it. So we're going to use coefficients. Coefficients are a number that can go in front of your reactants individually, or it can go in front of your product as a whole, but it doesn't ever go in between. And it is not I lost my number, a subscript. Is that what they're called? Yeah, subscript. Subscripts are these little numbers that go down below. They might be different numbers, but these never change. You cannot change the subscripts, okay? What you can change is the number that you put in front, which is called the coefficient. Really big word, or for just to explain what we're going to multiply this by to make it balanced and even, okay? So if we wanted to figure this out, what we could do is we could put a coefficient right here, turn this into 2 H2O. This is basically like this, right? The whole thing gets multiplied by 2. So then all of a sudden we've got 4 of the H's. And we've got 2 of the oxygens, correct? Because we've multiplied the 1 by 2. And that's all going to be in 1. And now, what do we need to multiply up here to make this balance? Well, we need to put another 2 coefficient up here in front of this guy in order to make this balance. So now we've taken an imbalanced equation and we've balanced it using coefficients. This sounds so amazing, and yet it was really easy, right? We got this. So just don't forget, never change the subscript. Those are not changeable, okay? All right. So we are going to look at different types of chemical bonding now, okay? So a chemical bond is a force of attraction between atoms or groups of atoms. I think we're going to read just a tiny bit here. The most stable electron configuration for atoms is when their highest energy level has a full set of electrons. That's important to know. So in our model, I love it at the very beginning of the chapter here. They review with us some of their famous people. And they said when you combine Dalton's atomic theory, which states that all matter is made up of atoms, and different substances are made from different combinations of atoms. And with Bohr's model, B-O-H-R, Bohr's, not boring, I'm sure. Bohr's model of the atom, which looks like this, I'm going to draw it, with electrons and energy levels, you can find out how different compounds will stick together, which is what this whole chapter really ends up being about. So here's Bohr's model. So this is our nucleus. Inside of our nucleus, we've got our protons and our neutrons. And you can have different numbers here. They don't have to match. But the number of protons you have will match what? Your number of electrons. So if I only have 2 electrons, or protons, I'm only going to have 2 electrons, which are out here. So this is my one. If I were to have 4, 1, 2, 3, 4, then I would have to have another one of these, because we can only put 2 on the first ring here of, oh, I'm forgetting my words here. Sorry. Energy orbital, I believe, something like that. So energy level, the numbers we should remember, this is kind of important because this is what they're talking about, is the first energy level can only have 2. So if it had only been 2 in just this first ring, then it would be full and complete, and it would be really solid and strong. With this one not being complete, because it can hold, I believe, 4, then 4 electrons. If it's not complete, it's not as stable, and definitely not as powerful. So let's get back to where we're at here. I'm on page 121. All right, so most stable electron configuration for atoms is when their highest energy level has a full set of electrons. Here they are. First energy level has only 1 orbital, so it can contain only 2 electrons. It's full when it has 2 electrons. Helium has 2 electrons, so it's stable. All the other energy levels are when they have a set of 8 electrons in them. So all the rest of the noble gases found in group 8A have a stable electron configuration with 8 valence electrons and therefore are not reactive. So when it's stable, it's not very reactive. It's not wanting to share electrons with other molecules. All right, so on and on and on. Here we go. Gonna get to the point. Chemical bond, force of attraction between atoms or groups of atoms. So we're going to look at some different types of those. Ionic bonds. So there's 2 main ways. One is sharing electrons, and the other is transferring electrons. So I think we're going to look at transferring electrons first, and ionic bonds. So so if an atom has the same number of electrons and protons, they are neutral. That's what we've been looking at so far. Sorry if that's in front of you. Some atoms do not have stable electron configuration. We'll achieve that by transferring electrons. They want to be stable. You may have guessed that if atoms give away or take an extra electron, then the atom will no longer be neutral. So what happens? Atoms that are not neutral will have positive or negative charge depending on whether they give away or take on extra electrons. Atoms with an electrical charge are called ions. So an ion is, write the word ion. Ion is an atom or a group of atoms that has a positive or negative charge, which really means in the end that they are sharing an electron or taking on an electron from another one. So here's another guy, his nucleus, and maybe he's giving one here. If this is full, or like this inner ring would have been full, if it was the outer one, it was like helium, only had 2 electrons, it can't take on another one. But if there's room, like this one made up molecule is, it could take on an extra electron. And which one is it? Does that make it positive or negative? This is, in my opinion, just slightly counterintuitive, because I feel like when electrons being negative, like they go somewhere, that would make it more negative, and that is actually true. I think it is. Let me think this through. So if you think about the fact that there's the same number of protons and electrons, if they lose an electron, it's a positive now. That's what I was thinking. It sounded weird to me because I feel like when it's putting out electrons, it should be negative, but really it's lost negativeness, right, by sending out that electron. So now if this one's giving away electrons, this one is more positive. This is a positive charged ion. If it's that's for this one here. But if it chooses to take one, we can't do both at the same time here. If it takes one on, it has more electrons than it has had protons before. So the negative is winning, so now it's negative. So over here, this example shows negative. If it was giving them away, it would be positive, because just think of what's got more in the end. All right, the positive, the negative. Who's winning? Okay, let's see here. So when they're positively charged, meaning they have given away some electrons. Let's stay over here for a second. Okay, so we're giving away. We're positive charged. That's my plus, which is a positive sign. Positively charged ion is called, I'm going to say it right, cation. Okay, this is a cation. When it is the other way around, And we have accepted more negative electrons, and is negatively, that's a negative sign, negatively charged ion. It is called, let me find my word, it is called an anion. There's more. There's all these little details about this that you want to know. I know you're like, yes, I always wanted to know this. This is so exciting. Here we go. So, when you have a positively or negatively charged ion, they not only have a special fancy word for it, but they have a special fancy way of talking about it and writing its name out. So they want you to know all this, so I'm going to show you. Here we go. So let's start with a cation. Don't say the other, it looks like cation, don't say it. It's cation. Symbol for, say, sodium ion is Na and then plus. If you don't see a number there, it's just assumed that it's like a 1, okay? It's just, the 1 is assumed. But you might see a plus and a number here, or to actually be a number then plus, number positive. And how many it's accepted. Let me see here. How many is given away, right? Because it's all about the electrons going away, making it positive. Okay, so the other thing that we do is we call it an ion in it. So we would say the element name and then like sodium ion. So that's how we refer to it. Sodium. You're like, but I thought you said it's a cation. Well, you got to still say the name of the actual element somehow when you're describing it. Yes, it's a, individually it's a cation, but as a whole, this is called, maybe you have a whole bowl full of salt. These are sodium ion. All right, so over here, they have the same thing. They have special ways of explaining it and or describing it as elements and the actual symbol. So anions, they take the first part of a name of their element and they add the suffix "ide" at the end. So Cl, oh no, work. Cl negative, that was supposed to be straight, is going to be chloride. And we would take, it would be a chlorine atom, but that was negatively, it was a negative ion or an anion, and we now call it chloride, and we still keep the word ion. It's a chloride ion. So, it says atoms of the elements in the halogen family all easily accept one extra electron. And so they will have a 1 negative charge, and we'll have names such as fluoride ion, bromide ion, and iodide ion. See that all the ides, they get the ides. This one just gets ion. And remember the pluses, the minuses, and sometimes it's going to be something like 2 plus, okay? We'll have different numbers, okay? All right, let's see what's next. Ionic bonds. Oh, this is where it gets really exciting. Okay. I don't mean to be, like, I actually think this is really interesting. I might doubt slightly whether or not I can actually explain this well. What time is it? 7. It's 7? No, you have to be there at 7:30. You're fine. And that's on your video. You're welcome. All right, you can see that over and over. Okay, so we're looking at ionic bonds now. So I'm going to erase this stuff. So what was that we were just doing? That was called just explaining ions. So now we're going to talk about ionic bonds. All right. My paper could possibly stay open for me and not closed. Okay, so chemical bond formed between oppositely charged ions. So we have a cation and an anion, or a positively charged ion and a negatively charged ion. If they are connected and bonded because they're probably attracted. Do you guys know, whoever's watching this, do you know that just like in electricity, we have like magnetic fields and stuff, we have pretty much the same thing. It is exactly the same thing because those are electrons as well. So we have positive and negative are attracted to each other. Okay, we're gonna give them a heart. They love each other. Okay, but the negative and negative, nope. It looks like nose and no, it's not. It's my sad face. And the positive, they do not like each other either. They want to repel each other. If you've ever put two magnets together and they either stick or they go boing and they fling apart, these are the ends. You must have a positive and negative together if they are sticking, and if they are repelling each other, it must be negative and negative, or a positive and a positive. All right, so and an ionic bond is when you've got this going on. And so this makes them neutral in the end. And so because they cancel each other out. All right, so they don't end up being positive or negative because they cancel each other out. Okay? So before we move on in the eternal module 4 that never ends, we're going to look at the electron dot diagrams, which are super cool because they allow us to illustrate the valence electrons, which are the electrons that are on the outermost ionic, energy level, or energy orbital, and without having to draw an actual Bohr model here. And so what we've got here are like their symbols. I'm going to erase all this. And then we've got little dots around it. So it's kind of cool. And they have some on page 127. They've done like a whole bunch of electron dot diagrams of group A elements. So that's pretty cool. So you can see that, like, we're going to look on the page before it. My markers just don't love me today. Na has one valence electron. What that means is that however many protons and neutrons in its nucleus, however many orbitals it has, on its outermost orbital, it has one lonely valence electron, and that's what that's showing right there. All right, so if we have an equation where we have Na dot plus chlorine, Cl, and Cl, they've illustrated by making dot dot, dot dot, dot dot, and then only one little dot right there. It's missing something, and this is really close, so I'm going to switch it over. Okay. All right, so we've got that, and then we've got our rest of our equation here. This dot, we're going to show the action here just for fun. I'm going to use a different marker. This dot, I keep calling it that. This electron wants to go right here. Why? Because when there's just one, it's not stable, and this isn't complete either, and it's a draw. It's an attraction there. So what happens is this electron jumps over to the chlorine, it accepts it, and by getting more electrons, it makes our chlorine now not only stable, because all of its orbital is now complete and full, but it makes it negatively charged. So we're going to give it a negatively charged ion symbol there, which makes it an ion, right? And then over here, we realize that sodium here has given up its valence electron, which makes it one less electron and one less bit negative, so it's more positive. So we've got over here Na positive charge, okay, which makes it a cation, right? So we're going to get those terms down, we sure are. So lead learner here, do not have all this down yet. So let's look at, that is called the dot diagrams, okay? So we might be using those dot diagrams as we go here. All right, so that's how they work, and I like that. I think that's kind of cool. It's like dot math or touch math. All right, covalent bonds. Covalent bonds are a chemical bond in which two atoms share one or more pairs, not parents, they're not mommies and daddies, pairs of valence electrons. Okay, so covalent bonds. Okay, so all of this is covalent bonds. I'm just going to keep this super, super simple. So say we have hydrogen, and this is its nucleus, and here's its orbital, and it's only got one electron, and then here's another hydrogen molecule, and it's, I should say, atom. This is an individual atom, this is an individual atom. Together they make a molecule, and say they share, he's got one electron as well, and they share, and this allows them to be stable, because how many can go on the innermost ring? The first orbital, and that is 2. So now that they have 2, they're much more stable together. So this would be like the first part of water, H2. So because there's 2 here sharing one electron each. All right, so this is called what? Covalent bond, right? All right. Did you know they can have multiple covalent bonds? What? Yes, they can. It gets more and more exciting. I'm telling you what. So can I draw this? I don't know. But let's see here. When they have a covalent bond, they do this sign for it. See, 2 chlorine sharing electrons and sticking together. Because of that, at the same time they stay together. That is called a covalent bond. If they have multiple, like 2, like they're sharing 2, that's what all it is sharing 2 electrons. They get a double covalent bond. You can have a triple covalent bond, and all it is sharing multiple electrons. Okay? Okay, donkeys. Let's see here. We've got so much going on, and you guys are doing great. And I'm just saying this, I'm making this for my son, but I assume I will share this with other people someday. Whoever is listening, thank you for being patient with me. I'm just doing my best here. All right, so a covalent bond in which the electrons are not shared equally is called a polar covalent bond. What is that? A polar molecule is a molecule that has a slight positive as slight positive and negative charges due to an imbalance in the way the electrons are shared. Okay, so anytime you have a compound made of only two different atoms held together by a polar covalent bond, and the molecule is then considered to be a polar molecule. Okay, so what do we want to say about that? They have a I think I'm going to see here. We're going to probably skip this part a little bit. Maybe I should just read it because I can't explain it. I don't think I should skip it just because I can't explain it. So what it says is polar means opposite in charge. And because electrons spend more time around the atom with a greater attraction for electrons when atoms form a polar covalent bond, the atom will have a partial negative charge. The atom with a lesser attraction for electrons will have a partial positive charge. So, I remember this now. See, I read this. I've been reading this over the course of a week, and now I'm like, oh, okay. So, it's an unequal sharing of electrons. So we're going to get more into the polarity as we go here. And so two other types are of bonds, I should stop covering you up, are metallic bonds. Metallic bonds are when the metal ions and the constantly moving valence electrons form a lattice-like structure held together by the metallic bonds. This is why metals are malleable, which is our old word we learned before, which is to bend without breaking. Like aluminum's super malleable. The second type of bond involves the polar molecules, which I was just struggling over a minute ago. So, for instance, polar compounds such as water are molecules that have a partial negative charge on one side and partial positive on the other side of each molecule. So